From space, the Indian southwest monsoon is one of Earth's most massive atmospheric events, an engine of dense, swirling clouds entirely disappearing the subcontinent below. The volume of moisture transported to the subcontinent hinges on thermal conditions in the equatorial Pacific. Cooling in these distant waters shifts the trajectory and intensity of the moisture heading toward India. This global teleconnection is driven by the phenomenon known as La Niña, or the little girl. Shifts in this region are a primary variable in India's agricultural output and water storage strategies, making it a critical focus for both national planners and competitive exam aspirants. Moving beyond rote memorization requires an analysis of the specific physical mechanics that move energy across the globe. La Niña is one extreme of the El Niño Southern Oscillation, or ENSO, a coupled cycle involving both the ocean and the atmosphere. El Niño is the warming phase associated with Indian droughts, while its counterpart, La Niña, brings intense Pacific cooling and surplus rainfall to the subcontinent. Climatologists monitor the central and eastern equatorial Pacific, a grid designated as the Niño 3.4 region. The thermal state of this specific water patch acts as a global weather control panel. La Niña begins when surface temperatures here drop significantly below historical normals. Because the oceans and atmosphere are coupled, a thermal anomaly in the Pacific guarantees a cascade of air pressure changes everywhere else. The foundational mechanism involves the Pacific trade winds, which naturally blow from east to west along the equator. Under normal conditions, these winds push sun-heated surface water toward Asia and Australia, where it pools in the western Pacific. During La Niña, these trade winds intensify, aggressively displacing massive volumes of warm surface water away from the coast of South America. This displacement creates a void in the eastern Pacific. To fill the gap, deep, cold water is forced to rise to the surface. This vertical movement is called upwelling. It brings freezing, nutrient-rich water from the ocean floor up to the surface. This wind-driven mechanical process creates the massive thermal imbalance characterizing the La Niña phase. To see how this affects India, we look at the atmosphere directly above these ocean currents. Air moves in vertical convection loops across the equator, known as the Walker circulation. The cold, upwelled water in the East Pacific cools the air above it, creating a high-pressure zone where air sinks and storm formation is suppressed. In the West Pacific, the warm water heats the air, creating a low-pressure zone. Moist air rises rapidly here, forming active storm clusters over Indonesia and Australia. Because La Niña amplifies this pressure difference, the entire system of tropical storms shifts further westward, pushing closer to the Indian Ocean. The Walker circulation acts as an atmospheric bridge, transporting the energy from Pacific cooling directly toward the Indian subcontinent. This westward shift in storm activity strengthens the Indian monsoon trough. This low-pressure system acts as a vacuum, pulling increased moisture from the Arabian Sea and the Bay of Bengal. This map from the IMD shows the typical onset dates of the southwest monsoon. During La Niña, the enhanced moisture pull accelerates the spread of these rains across the subcontinent. When these winds encounter the Western Ghats and the Himalayas, they are forced upward, cooling and releasing surplus rain. The Niño 3.4 index for 2020 through 2022 highlights a rare triple dip anomaly. The cooling in the Pacific persisted for 3 years, leading to consecutive seasons of above-normal rainfall. While predictive models correctly forecast a national rainfall surplus during these years, predicting regional variations remains a significant challenge. Localized factors like the Indian Ocean Dipole, or IOD, can either amplify or dampen the moisture signal sent by La Niña. La Niña strengthens the monsoon's global engine, but variables like the IOD dictate which specific regions receive a harvest-saving surplus versus destructive flooding. These atmospheric shifts translate into tangible socioeconomic outcomes across India. Surplus La Niña rainfall provides critical irrigation for rain-fed agriculture, leading to significantly higher yields for kharif crops like rice and cotton. Higher agricultural production helps stabilize national food prices and can reduce overall inflation. However, the same intensity that supports agriculture can also result in fatal excess. La Niña events are historically linked to catastrophic flooding and infrastructure damage, particularly in the northeast and southern India. There is also a winter teleconnection. La Niña often corresponds to severe cold waves across northern India between December and February. The same cooling cycle that powers India's economic growth through record harvests also triggers its most consistent flood risks. For exams, focus on 3 high-yield concepts. First, ENSO is a coupled system of ocean and atmosphere. Second, upwelling drives La Niña, as winds pull cold water to the surface. Third, positive correlation. La Niña mathematically links to a stronger monsoon and surplus rainfall. This is the direct inverse of the El Niño correlation, which results in atmospheric subsidence and drought. Applying this mechanistic framework allows an observer to track a wind shift in the Pacific and deduce the likely outcome for the fields of South Asia.